Morning, everybody. So any questions before we start? Nothing? Oh yeah, I got you. Yeah, definitely. Yeah. After the lesson? I got you. I got you. All right. Anybody else? Y'all good? I don't know yet. All I did was I made the answer key. Yeah, but definitely I'll have it done by next week, and then the week after y'all get it back. Yeah. Yeah, because next week we don't have class. Yeah. It's another holiday. Yeah, tutoring still on. Yeah, 12 to 6. Same thing in person and online. No change. Yeah. You make an appointment. No, like last week, you make an appointment. I made it for 1 o'clock. After class, actually, last Saturday, I made it for 1 o'clock. Yeah. Where do they send you a link to your email? Yeah, there's a confirmation email, and then there's a link inside the confirmation email. All the way. Yeah. It's to the email that you signed up with. You know, like that same email that you used to log into WC, right? That's where they send it to. Yeah. Yeah, but it was all open Wednesday, Thursday. They flipped the time. Friday was open, but they flipped the time for Wednesday, Thursday. They made it 12 to 6. That's the only thing. But they still had in person. They still had online. You know, the whole campus was open. You know, they just filmed a movie yesterday. You know? Yeah, I don't know what movie it was though. I was curious. I wanted to ask. You know? Yeah. Yeah, they got a lot of TV shows and stuff that they do on campus. You know, you ever seen that movie, The Greatest Showman, with Hugh Jackman? Like that was here. No, Hugh Jackman. Hugh Jackman was in there, and what's that other guy named Zach Efron or whatever? Like he was here. Efron, yeah, him and Zendaya. Yeah, they was all here. Yeah. So that was filmed over here. You know, and a whole bunch of TV shows and all that too. Quantico, all that. Yeah. Quantico was here. Beautiful Mind was here. That old movie. You know. Yeah. Yeah. I mean, ask them. So there's a major here for like film and media and stuff. Like they get to work on that stuff. Yeah. But you know that work is overnight work though, because they only shoot at night. You know, like right now they packing up. Yeah. All right. So if there's no questions, let's jump into it then. All right. Today should be fun. That's what we're getting into right now. Make sure I'm recording. Everything good? Okay. So we're gonna have an introduction to random variables and probability distributions. This is gonna be dope. All right. So let's talk about a random variable real quick. All right. So for our purposes, we say that a statistical experiment or observation is any process by which measurements are obtained. For instance, you might count the number of eggs in a robin's nest or measure daily rainfall in inches. It is common practice to use the letter X to represent the quantitative result of an experiment or observation. As such, we call X a variable. All right. Just laying the groundwork real quick. Okay. All right, so let's talk about a random variable. I'll give y'all the definition. So a quantitative variable, remember quantitative is numbers, right? A quantitative variable X is a random variable if the value that X takes on in a given experiment or observation is a chance or random outcome, right? So we have two kinds. We have a discrete random variable that can take on, only a finite number of values or a countable number of variables, right? So when I hear discrete, I think about countable, right? A continuous random variable can take on any of the countless number of values in a line interval, all right? So continuous, just think of it as it doesn't stop, right? But discrete, countable.
Right? Oh, like discrete have a finite amount of things you can count.
Exactly. And it just keeps going. All right. All right. So the distinction between discrete and continuous random variables is important because of the different mathematical techniques associated with the two kinds of random variables. In most cases, we will consider a discrete random variable will be the result of a count, right? The result of a count. Remember that. The number of students in a statistics class is a discrete random variable, right? Values such as 15, 25, 50, and 250 are possible, not in BCC. However, 25.5 students is not a possible value for the number of students, right? So we don't count babies here. All right. Most of the continuous random variables we will see will occur as a result of a measurement on a continuous scale. So for example, the air pressure in an automobile tire represents a continuous random variable. The air pressure could, in theory, take on any value from 0 pounds per inch squared, PSI, to the busting pressure of the tire, values such as 20.126 PSI or 20.12678 PSI, and so on and so forth, right? Something that we should also notice here, right? I don't know if this kind of helps, like whole numbers, right? So discrete has whole numbers, whereas continuous has like decimals, right? I don't know if that helps. Yeah. Bless you. But the idea is that if you're counting something, 1, 2, 3, 4, 5, 6, 7, that's discrete. All right, let's look at an example real quick. Help y'all out with your homework right now. All right. So this one says, which of the following random variables are discrete and which are continuous? So measure, keyword, the time it takes a student selected at random to register for the fall term, right? So time can take on any value. So this is a continuous random variable, right? Counts, keyword, the number of bad checks drawn on a upright bank on a day selected at random. So the number of bad checks can be only a whole number, such as 0, 1, 2, 3, so on, right? And this is discrete, right? Mm-hmm. All right, let's look at two more real quick. Good examples, good examples. Measure, keyword, the amount of gasoline needed to drive your car 200 miles. So we are measuring the volume, which can assume any value. So this is a continuous random variable. Pick a random sample of 50 registered voters, right? How many? 50, 1, 2, 3, 4, 5, 50 in a district, and find the number who voted in the last county election. This is a count, so the variable is discrete. And that's it. Very simple.
When you see like the word pick and like pick that
right,
it will be
discrete. It's word continuous, right? Mm-hmm. So like anything that's like scientific experiment observation, right? Think of that as being like continuous, right? But discrete is like strictly a count. It's gonna be a whole number, you know? Right. All right. So let's build on that, right? So what we want to do is we want a probability distribution of a discrete random variable. So a random variable has a probability distribution whether it is discrete or not, or continuous, right? And that's what we're building up to right now. Real quick, let's just talk about what a probability distribution is. Oh, that's a new word. All right, so a probability distribution is an assignment of probabilities to each distinct value of a discrete random variable, or to each interval of values on a continuous random variable. All right, that's a probability distribution. Let's talk about some features of it. All right, so some features of the probability distribution of a discrete random variable. The probability distribution has a probability assigned to each distinct value of the random variable. The sum of all the assigned probabilities must be 1. So we still have that rule, right? Or the sum of all probabilities equals 1. That hasn't changed. Got you. Sorry. I feel like I'm blocking you. Am I blocking you? Or are you good?
Let's stay right
I wish I could just move this like an inch that way. They have to like undrill that and just like drill it more. I guess it's because of this why they don't do that for the light. But, old building, old building. All right, let's look at an example real quick. All right. So Dr. Mendoza developed a test to measure boredom tolerance, right? Sounds psychological. He administered it to a group of 20,000 adults between the ages of 25 and 35, right? The possible scores were 0, 1, 2, 3, 4, 5, 6, with 6 indicating the highest tolerance for boredom. These are super people, right? The test results for this group are shown in the table, right? If a subject is chosen at random from this group, the probability that he or she will have a score of, let's say, 3, right? According to the table, would be 6,000 out of 20,000, or 0.3. And in a similar way, we can use relative frequencies to compute probabilities of other scores. So let me show you the table real quick. Show you where that came from. So here we go. So let's talk about this real quick, right? So for 6.1 right here, right, the boredom tolerance test scores, right, for 20,000 subjects, right? How did they get the likelihood that a score of 3 would be boredom, right? What they did was you have the counts, right, of how many people would be bored. Like if they gave you a score of 3, right, it's 6,000. So you simply just take the 6,000 and divide it by the total, the 20,000. And that's it, right? Now, for me, I'm not really interested in the decimal. You could leave it at 6,000 over 20,000 and we good, all right? If you want to type it in your calculator, go right ahead. No pressure though, all right? 6.2, sorry, probably distribution of scores at boredom tolerance test, right? So this, right, is the probability, right? When you type it in the calculator, the decimal, right, is right here where it says probability P of X, right? This column right here. right? So all they're doing is they're taking each number for the number of subjects, like for the first one is 1,400, right? And they're just dividing it by the 20,000. And that's how they get the 0.7, right?
Wait, I'm sorry, what is PNM?
Probability. It's the probability of the scores here occurring, right? So a question that they might ask you is, Mhm. Go ahead. And so a question that they might ask is like saying, what is the probability that somebody, or no, that the test result is a 3, right? So the answer could be 6,000 over 20,000, or it could be simply just 0.3. And that's it. That's the whole thing. You know? Maybe they might ask you something like, oh, what's the likelihood that they gave you an answer that was like 5 or better, right? So 5 or better, all you do is you just add these two together and we're done. Sure.
So you don't care if you put like a fraction or dozen.
Yeah, I like fractions more than decimals. Oh yeah. You see the whole example? Got you. Yeah. Mhm. This is the cool stuff.
Question.
Go ahead.
The 14,000, 14,000 number, so.
The 1,400. You see?
How we get that one?
They did that for us already. They like that was given to us.
Okay.
Yeah.
But like the
So-
question itself is like 6,000 over
So-
over 20,000.
Right. So the total, which is given to us, is 20,000, right? And then this is the success that we're looking for.
Okay, so
Right.
if randomly they say the success that we're looking for is 3,600, then it'll be 3,600 over 20,000.
They would ask you what's the probability of 2,
Oh, okay.
and then the answer would be 3,600 over 20,000. Yeah. They always give you the table. Yeah.
So what's the probability of 2?
Yeah.
Side numbers.
Right. Yeah. Like this table, the probability distribution, they probably won't give you that. Sometimes, not all the time.
Well,
Yeah.
sometimes then I give you the total, right? Then I.
They'll always tell you that. Always. Yeah, you'll always have that information. Yeah. This table right here though, the 6-2 table, right? Remember we were talking about histograms before? You can actually graph this on a histogram, right? Let me show y'all what that would look like real quick. Probability is the Y, and then the X would be like the 0, 1, 2, 3, 4. Right?
Dependent on the other
Right.
the X value is independent.
Yeah. So this is how it would look if we were to graph it, right? So these are the tolerance scores, 0, 1, 2, 3, 4, 5, 6, etc. This is our probability, right? And then this would be the histogram that is associated with it. Just want to show you guys about that possibility. Yeah, please. Go ahead.
Yeah. Yeah. Now we and the homework is in Chinese. You're like, oh, so
It's gonna be good, I promise. It'll be good.
101 tries.
Something to notice about this real quick. Just want to point something out, right? Notice that the scores here, right? They're midpoints, right? So they're in the middle of each bar. Just wanted to like point that out to everybody. Right? Midpoint in the middle of the bar right here. That's all I'm trying to say. Yeah. Oops. I'm sure you passed. All right. So these probability assignments make up the probability distribution. Notice that the scores are mutually exclusive. No one subject has two scores, right? The sum of the probabilities of all the scores is 1. Just want to highlight that, right? See our probabilities right here? We add them all up, the sum is equal to 1, right? Just wanted to show that. So the graph of this distribution is simply a relative frequency histogram, right? In which the height of the bars over the scores represents the probability of that score, since each bar is 1 unit wide. The area of the bar over a score equals the height and thus represents the probability of that score. Since the sum of the probabilities is 1, the area under the graph is also 1. The top-notch clothing company needs to hire someone with a score on the boredom tolerance test of 5 or 6. So to operate the fabric press machine, since the score of 5 and 6 are mutually exclusive, meaning what? No. Mutually exclusive meaning that they keep going with that. They no, they can't. What?
Say it out, they can't work without each other.
No. You're closer. You're closer. They can't. What? That's closer. I'll take that. They can't occur together. Occur together.
Oh, they can't work together.
Right. Right. So you can either have a score of 5 or you can have a score of 6, but you can't have a score of 5 and 6. Right. So mutually exclusive, they don't work together, right? The probability that someone in the group who took the boredom test made either a 5 or a 6 is simply just the sum of that. So the probability of 5 or 6 is equal to the probability of 5 plus the probability of 6. Add them together, and that's your answer. All right?
I'll let you go right.
Yeah. So that's all that is. Simple stuff. Bring
This
it.
is all question.
That's what I just feel like.
Yeah.
I'm sorry,
Yeah.
I just feel like statistics is like a whole bunch of words, like.
What you mean?
Like, it's just mad extra, like the words confuse you and then they'll probably so simple.
It is simple.
Yeah.
That's why psychology is so simple.
Yeah, cause
You know?
it's a bunch of confusion. That's what it is, a bunch of confusion, like that's.
I mean, you should.
That's a whole paragraph, just to sum it up, just to say 5 plus 6.
Yeah.
Excuse me, like just say, what is the sum of 5 plus 6?
And this is why lawyers get paid so much money.
It's true.
Yeah.
You know,
Mhm.
because they be doing stuff like this. You know.
Lawyers that people want to, nobody wants.
Mhm. Yep. So notice that you find a probability of 5 or 6, right? We could simply add the areas of the bars over 5 and over 6. 1 out of 10 of the group who took the boredom test would qualify for this position at top-notch clothing, right? Or 10%. Good stuff. Good stuff. All right. Let's talk more. So probability distribution can be thought of as a relative frequency distribution based on a very large N, right? Remember, N is our sample size, right? A very large sample size. As such, it has a mean and a standard deviation, right? So if we're referring to the probability distribution of a population, then we use Greek letters, right? Like mu over here for the mean and sigma for the standard deviation, right? Yep. That's how we do it. These are lowercase mu, lowercase sigma, by the way. So when we see the Greek letters used, we know the information is for the entire population rather than just a sample, right? If we have a sample probability distribution, we use X bar, right here, and S respectively for the mean and the standard deviation. And all of that is on your formula sheet. All right. For the mean and standard deviation. you're wondering where I am, I'm in chapter 6 on your formula sheet
Oh,
for today.
Oh,
Yeah. I got you. Oh, by the way, y'all could totally use your formula sheets to do your homework, you know. So y'all
we
know.
only got to do the we kinda got to do the neighbors.
You know what? I should probably mention this too, in case anybody didn't tell y'all. So I realized next week, Saturday, we don't have class, but also next week, Monday, like the campus is closed. Yeah, not this Monday, one after, you know? Yeah, yeah, but this is like closed, like, you know, tutoring, like can't come on campus and run around the track, like nothing, like closed. You know? It's like a real day off. Yeah.
They use all these tables.
You want to, I don't like tables. I don't like tables. I mean, we gonna talk about it. Like I'm gonna show you the table, but yeah,
Crazy.
I'm gonna show you the table, but I don't like tables. I'll be honest with you. I mean, y'all got the calculators right now, so that's what I'm about to really get into. That joint is fire. All right, so check this out, right? The mean and the standard deviation of a discrete population probability distribution, excuse me, are found by using these formulas. Right? So we have mu is equal to the sum of x times p of x, right? Mu is called the expected value of x. Remember that word, expected value, right? Sigma, right, is equal to the square root of the sum of x minus mu squared times p of x, where sigma is called the standard deviation of x, right? All on your formula sheet, by the way. So where x is the value of a random variable, p of x is the probability of that variable, right? And the sum, sigma, is taken for all the values of the random variable, right? So what does that mean? Blah, blah, blah. You add up all the x's, just like we did before, right? So all this is just a bunch of addition, right? So note, mu is the population mean and sigma is the underlying population standard deviation because the sum is taken over all the values of the random variable, i.e. the entire sample space. Go ahead, what was your question? When you see the example, it'll make sense. It's like really, really simple. But how you get to it is really interesting. It's really, really interesting. I want y'all to be like real strong in y'all majors. You know, everybody here get their PhD and they be good. You know, yo.
I barely make it through the squads.
Of course, I think everybody here gonna get a PhD. You know, yeah. Was so let's see. The mean of a probability distribution is often called the expected value, right, of the distribution. This terminology reflects the idea that the mean represents a central point or cluster point for the entire distribution. Of course, the mean or expected value is an average value, and as such is need not be a point of the sample space. The standard deviation is often represented as a measure of risk, right? A large standard deviation implies a greater likelihood that the random variable X is different from the expected value mu, right? So blah, 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 right? Y'all about to take a bet. Y'all see a large standard deviation. Y'all taking a bet? Nah, right? Because it's going to be a likely chance that you're not going to get your expected value out, your expected result out.
It's not the same thing as margin of error.
It is.
It is.
Mm-hmm. All right. So low key, this is how we stop gambling in life, right? Look at the standard deviation. Yeah. Speaking of which, though, how about that New York Liberty? I feel like nobody watches that but me. I be asking everybody, like, damn. They good though, man. They in the Final Four. Yeah, lady basketball. Yeah. Yeah. That's the New York team. Like we killing it, yo. Yeah. Well, they gotta win this game, then they gotta win the next 4 games or whatever. Yeah, the Yankees and the Mets, right? Yeah. Yo, that Met, like that last hit, man, ninth inning, that was real. Yeah. You think so? We'll see. We'll see. All they need is one good game, right? Like one set of good games. They don't need to be the greatest, right? To get there. All right. Expected value standard deviation. Are we influenced to buy a product by an ad or by an ad we saw on TV? So national can't even say that word. How you say this word? Infomercial. Thank you. Lord Jesus, man, having a brain fart. Marketing Association determined the number of times buyers of a product had watched a TV infomercial before purchasing the product. So the results are shown here. All right. So we have the number of times buyers saw the commercial. I'm just gonna say commercial because infomercial is crazy, right? How you say it in Spanish? Oh man, I'm lost. I'm trying. All right, so this is the number of times that they saw it, right? 1, 2, 3, 4, and I guess 5 is like could be more, right? And then the percentage of the buyers, right? So this is how many people saw like the infomercial, right? The ad one time. 27% of them decided, you know what, I need that product. They went out and they got it, and then so on and so forth. All right.
Because e-commerce.
Yeah, so it's like a commercial. Right. Yeah. Got you. Yeah. So the star is saying that like they could have seen it like 6 or 7 or 8, So they just kind of like lump them all together just to make a nice little chart, basically. All right. So those you study in marketing, like yeah, we use statistics in marketing too. Low key, marketing is just applied psychology.
Yeah.
That's all it is. Right? So we can treat the information shown as an estimate of the probability distribution because the events are mutually exclusive. What does that mean again? And the sum of the percentages is 100%. So if I add up all these percentages here, 27%, 31%, et cetera, right? Add them up, it's going to equal 100%, right? So we always have that rule. So now they're asking us to compute the mean and the standard deviation for this, right? And luckily for us, scroll up here, we have 2 formulas to do that. All right. So let's take a look. Both, yeah. Because I want the mean and the standard deviation. All right. So what we're gonna do, right? We're gonna put our numbers into a chart, right? I'm gonna show y'all the chart because my handwriting is not so pretty. Right? But it's not that bad. So bam, right? I promise you it's not that bad. Let's go through it real quick. So we have the number of times buyers view infomercials before making a purchase, right? So X, this is our number of viewings. Just like how we had the table above, the 1, 2, 3, 4, 5. Here you go, right here. 1, 2, 3, 4, 5. And then we have our probability of the buyers actually buying the product, right? So that's like a 27%, 31%. Right. So that's gonna be your first two columns right here. Right? I didn't mean to do that. Where's my pen? On my highlight. There we go. My pen. All right, there we go. All right, anyway, right? The next column, right? This column is X times P of X, right? So what am I doing to get this column? I'm taking the first column number, right? And I'm multiplying it, right? So this is like 1 times 0.27. And that's how I got that. The next one is like 2 times 0.31. And that's how I got that, etc. Right? Now, after I get this column, the X times P of X, if I sum it, just add up all that whole column together, right? So add the column. Right? That's how you get the mean right here. You just add all these numbers together, 0.27, 0.62, etc. Just add them together, and you're gonna have the mean, which is 2.54. Right? And that's how you find the mean. Multiply the numbers together, add them up.
Add them all up.
Yep, that's it. Right? Now, let's go on to the standard deviation. So to find the standard deviation, this column right here, right? We're taking the X value, in this case the 1, and we're going to subtract it from the mean, right? So to get this first number right here, right? The negative 1.54, that's simply just what? 1, exactly, minus the 2.54. And that's how you get the negative 1.54. The same thing again, right? So the next one will be 2 minus the 2.54. Right?
Oh,
Yeah.
2.54 is there.
Yeah. You did. Where'd I lose you?
We lost 2.54, but now I saw 2.54.
So look, this is the mean right here, right?
Yeah.
To get the mean, all we did was we added up this column, right? Okay. So now I'm on this column right here.
No, but the first column.
The first column, this one. So that is just copying. That's from the chart that we got up here. Yeah, there's nothing there. So the second column is this part.
No, that's. You're confusing yourself.
Yeah. So the third column, right? What you're doing is you're taking everything in the first column and multiplying it by what's next to it.
Okay.
You know, so the first one is like 1 times 0.27 is 0.27. You know, and then the second one is like 2 times 0.31, 0.62. Then when you have this entire column, you add it together. Just on the calculator, just add them, right? Like 0.27 plus 0.62, etc., right? When you add it all together, that's how you get the mean, right? Which is right here. This is the mean in this box right here. Right?
You just add them all together, or you don't.
That's it. No divide, just add. That's it. Yeah. Mu means population mean, right? Population mean. Yeah.
Like, I feel like this is all helpful because obviously you're speaking, but like, for like the homework, I think you should do it like in class and like people should go up.
Yeah, that's what we do at the end.
But people should go up on the board. Because
Sure.
when you're doing it, like ourselves, we kind of like pick it up more
Gotcha.
versus like, you know.
Sure. At the end of class, we could definitely do that.
Yeah.
I got you.
Yeah. People that don't know.
I
mean,
feel like
y'all all got it. Y'all all got it. So at the end of the class, if y'all want, we got 2 boards.
Yeah.
We got the markers. Yeah. Yeah. So we have more practice. Yeah.
All
I
that
got
effort.
you. Got you.
If you like 100 tries.
Nah.
Like
You good?
30 tries.
Good. So stay after class. Stay after class and do it. Stay after class and do it. Yeah. Yeah.
Yeah, I mean, like the words, like it's
Yeah.
just very confusing, and it's only until you do it
That you
that you're like,
remember.
okay, this is kind of easy. Like when you like, you
Got
like,
you.
practice it yourself.
I got you. I got you. All right, we'll do that.
They start with cycles.
I got you. I got you. I'm gonna incorporate that. I'm gonna incorporate that. All right, real quick. I'm on this column now, right? So this is the x minus mu. So what I'm doing is I'm taking the x value, right? So for example, the 1, right? And I'm subtracting it from the mean, which is the 2.54. And that's how I'm getting the negative 1.54. Right? Yeah. The next one underneath it, you know what? Hold on, let me do one of these. 2 minus 2.54. The mean again, right? And that's how you get the negative 0.54, right? And then so on and so forth. Next one would be 3 minus the 2.54. And that's how you get the 0.46, etc., etc., etc. Right? So that's the fourth column. The fifth column right here. Real simple. Whatever answer you got over here in the x minus mu, square it. Right? Straight calculator work, right? So for this one, this would be like negative 1.54. In parentheses, the same way that I wrote it here, squared. That gives you that number. Right? Next one, very simply, negative 0.54. And then square it, and that gives you that number. Right?
So how is it?
Not the mean. It's going to ask you what is the mean and what is the standard deviation.
Of the chart.
Right.
Okay.
Yeah. Or they might throw other vocabulary at you. They might be like, all right, what's the expected value in the standard deviation?
Say mean, you know, they put everything divided by whatever. That's what like
Got you.
people get.
So that's true if you have a sample of data, but not for a probability distribution. Right. And that's the difference with
And
it.
that's because everything is already like
Given to you.
one.
Right.
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 That makes
You know? But you'll notice the difference in the questions though. Yeah, and like towards the end of the class, like that's when I'm gonna start pointing that out to you. You know? So
So
like
we know what chapter we're on and
Right.
specific question.
Right.
basically.
Yeah.
So
There's key words to it. Mhm.
the last number they give me 1.
Which one?
2.372. 372, right?
Yeah,
They give me 2.371.
that's fine.
That's not.
Yeah, that's fine. Yeah, so like this chart is rounded off. So your calculator is more accurate than the chart. You know, so that's why that is. Last column, right? Very simply, whatever you got in the fourth column, you're gonna take that and multiply it times the p of x. Right? So this first one is gonna be the 2.372 times the 0.27. And then that's how you get this. The next one would be like 0.292 times the 0.31. And that's how you'll get this number, etc. Right? After that, when you get the column, you're gonna add everything in the column. When you add everything in the column, you get the variance. Right? You get the variance, right? So this one would be sigma squared. Nope. Because the question didn't ask you for the variance, the question asked you for the standard deviation. So after you get that sum, you then square root the variance. Right? Square root the variance. So we're going to square root the 1.869, and then that'll give you whatever your answer is. Right? Always remember, for standard deviation, we square root the variance. Right? Same is true before, same is true right now. And that's it. That's how we do this. Not so bad, right?
Yeah.
Mhm. Mhm.
But when you square, where is the result? Like, you know,
I got you. I'm gonna show it right now. You got it?
You see the,
You mean the 1.54? You want me to leave that up there? Oh, I got that. This one is 1 minus 2.54. Just like that. And then this one is 1 times 0.27. Just like that. All right. All right. So for our mean, mu, right? We got the sum of x times p of x is equal to 2.54, right? Right underneath column 3. And then to find a standard deviation, we take the square root of the sum of column 6, as we're saying over there. So the square root of 1.869 is about 1.37, right? Your calculator will be more accurate than that, right? Yeah. It's a 6 column, right? 1, 2, 3, 4, 5, 6. Yeah. Yep. So that's that. Let's put some meaning onto this though. All right. So what does a discrete probability distribution tell us? A discrete probability distribution tells us the complete sample space on which the distribution is based, the corresponding probability of each event in the sample space. Formulas tell us how to find the expected value mu and the standard deviation sigma of the distribution. Very simple. So we have seen probability distributions of discrete variables and the formulas to compute the mean and standard deviation of a discrete population probability distribution. Probability distributions of continuous random variables are similar, except the probability assignments are made to intervals of values rather than to specific values of a random variable. So we will see an important example of a discrete probability distribution, the binomial distribution, in the next section, right? And one of the continuous probability distributions in chapter 7, right? When we study normal distribution. All very, very simple. So let's talk about binomial probabilities. Binomial probabilities. So we get into it. Before we talk about that, we got to talk about a binomial experiment. All right. So let's take a look at that. Chapter 6 is deep. Yeah. Remember, we learning now how to gamble, so we gotta go through it. So on a TV game show, each contestant has a try at a wheel of fortune. All right. The wheel of fortune is a roulette wheel with 36 slots, one of which is gold. So if the ball lands in the gold slot, the contestant wins $50,000. No other slot plays. What is the probability that the game show will have to pay up the fortune to 3 contestants out of 100, right? So in this problem, right? Yep, in this problem, the contestant and the game show sponsors are concerned about only 2 outcomes from the Wheel of Fortune. The ball lands on the gold or the ball does not land on the gold, right? That's the binomial right there. It's either you win or you lose, right? This problem is typical of an entire class of problems that's, we will see. Are characterized by the feature that there are exactly two possible outcomes for each trial of interest. These problems are called binomial experiments or Bernoulli experiments, after the Swiss mathematician Jacob Bernoulli, cool dude, who studied extensively in the late 1600s. I guess he's still alive. All right. So features of the binomial experiment. Let's talk about that real quick. Right, so there is a fixed number of trials, and we denote this number by the letter n, right? So sample size, right? The n trials are independent and repeated under identical conditions. Each trial has only two outcomes: success, denoted by S, and failure, denoted by F, right? So probability of success by P and that of failure by Q. So since each trial result is either success or failure, right? Probability of success P plus probability of failure Q, when you add them together, must equal 1, right? And similarly, right, the probability of failure Q is 1 minus the probability of success, all right? It's all in your formula sheet, by the way. Just talking. So the central problem of a binomial experiment is to find the probability of R successes out of n trials, right? That's what we're trying to do, find R successes out of n trials. And I know when you see it, you're gonna be like, all of that just for this? I know. Let's take a look, an example. So binomial experiment. So let's see how the Wheel of Fortune problem meets the criteria of a binomial experiment. We'll take the criteria one at a time. All right, one at a time. All right. Let's take a look. So each of the 100 contestants has a trial at the wheel, right? So there are n equals 100 trials in this problem. Assuming that the wheel is fair, right? Because sometimes they could jack up the wheel, right? Assuming that the wheel is fair, the trials are independent, since the result of one spin of the wheel has no effect on the result of the other spins, right? We are interested in only two outcomes on the spin of the wheel. The ball either lands on the gold or it does not, right? Let's call landing on the goal success, right? And not landing on the goal failure. In general, the assignment of the terms success and failure to outcomes does not imply good or bad results. These terms are assigned simply for the user's convenience, right? So success is simply just what you're looking for, right? It doesn't mean win, it doesn't mean loss. It's what you're looking for, right? Failure is just what you're not looking for. That's simple. Right? All right, so on each trial, right, the probability P of success landing on the gold is 1 out of 36, right? So there's one gold slot and there's 36 total possibilities, right? Since there are 36 slots and only one of them is gold, consequently, the probability of failure, right, Q, probability of failure, is equal to 1 minus the probability of success, or 1 minus 1 over 36, which is 35 over 36, okay, on each trial. So we want to know the probability of success of 3 successes out of 100 trials. So let's say that R, remember R is our number of successes equal to 3. In this example, it turns out that the probability the quiz show will have to pay the fortune to 3 contestants out of the 100 is about 0.23%, right? Or no, 0.23 or 23%, sorry. Later in this section, we'll see how the probability was computed, right? Big payout, big payout. What I don't like about the lottery is that they will divide your winnings with other people that won too. It's whack, yo. Yeah. Yeah, like if you won the Powerball and I won the Powerball, we gotta split that joint. You know? Mad whack.
I'll take whatever right now.
You take whatever. But I'm saying I could have had $1 billion and now she gotta get 500 million, I get 500. And then on top of that, we gotta pay individual taxes on both. You know, like yeah, terrible, terrible. All right. Anytime we make selections from a population without replacement, so I don't put it back, without replacement, we do not have independent trials. However, replacement is often not practical, right? So if the number of trials is quite small with respect to the population, we almost have independent trials, and we can say the situation is closely approximated by a binomial experiment. For instance, suppose that we select 20 trillion bills at random from a collection of, what was that, 10,000 bills, right? Issued at one college, and observe if each bill is in error or not. If 600 of the 10,000 bills are in error, then the probability that the first one selected is in error is 600 out of 10,000, or 0.06, right? If the first is in error, then the probability that the second is in error is 599 over 9,999, or 0.0599. Even if the first 19 bills, sorry about that. Even if the first 19 bills selected are in error, the probability that the 20th is also in error is 581 over 9,981, or 0.0582. All these probabilities round to 0.06, and we can say that the independence condition is approximately satisfied, right? So even though the math of them are different, they're rounding to the same likelihood, the same outcome. It is, but it's fun. It really is. Wait till you see the questions. It's mad simple. So next we will see how to compute the probability of R successes out of N trials when we have a binomial experiment, right? And I know there's a lot of words, but like real simple, like dividing two numbers. I know. But we got to understand where it comes from. Right? All right, so computing probabilities for a binomial experiment using the binomial distribution formula. Yay. So the central problem of a binomial experiment is finding the probability of R successes out of N trials, right? Now we'll see how to find these probabilities. Suppose you are taking a timed final exam, right? You have 3 multiple choice questions left to do, right? That ain't this class. Each question has 4 suggested answers, and only 1 of the answers is correct. You have only 5 seconds left to do these 3 questions, right? So you can think of this as a tease exam, right? You have only 5 seconds left to do these three questions. So you decide to mark answers on the answer sheet without even reading the question. Assuming your answers are randomly selected, what is the probability that you get 0, 1, 2, or all 3 of the questions correct? All right. So you're just choosing any answer at random, and we're trying to win right here. All right, so here we go. That's how you figure that out. It's going to tell you if you should be guessing on tests or not. All right. So this is a binomial experiment. Each question can be thought of as a trial. So there are N equals 3 trials. right? The possible outcomes of each trial are success, S, indicating that you found the correct response, or failure, F, meaning that you got the wrong answer, right? The trials are independent. The outcomes of any one trial does not affect the outcomes of the other. So what is the probability of success on any one question? Since you are guessing and there are 4 answers from which to select, the probability of a correct answer is 0.25. The probability Q, so probability of failure of a wrong answer, is then 0.75. In short, we have a binomial experiment where we have n equals 3, that's our trials, right? We have our probability of success 0.25, and we have a probability of failure 0.75. Now, what are the possible outcomes of the terms of success or failure for these 3 trials? Let's use a notation SSF, for example, to mean success, success, and failure, right? To mean success on the first, success on the second, and failure on the third. So there are 8 possible combinations of success and failures that are, right? Here they are. So either we could get all 3 questions right, success, success, success. We get the first 2 right and the last one wrong. We get the first one right, the middle one wrong, the last one right, you know, so on and so forth, all the way down till we get all of them wrong, right? So this is our sample space. This is the possible outcomes that could happen when we guess those last 3 questions on our test, all right? So to compute the probability of each outcome, we can use the multiplication law because the trials are independent. For instance, the probability of success on the first 2 questions and failure on the last is the probability of success, success, failure, and is equal to the probability of success times the probability of success times the probability of failure, right? Where you just plug in the numbers, right? This is going to be 0.25 squared times 0.75. That's just the calculator, right? You're just multiplying the possibilities together. That's all you're doing here. This is like an AND question from last time, right? So probability of success and success and success, or in this case, probability of success and failure, right? So in a similar fashion, we can compute the probability of each of the 8 outcomes, right? So these are shown in a table, right? So table 6, 8, right? Along with the number of successes are associated with each outcome. So let's take a look at that table. Not asking you to draw the table, just showing you the table real quick. So here's our table right here. Right? So this is outcomes of a binomial experiment, right? Where n is equal to 3, right? So here we go. We get all 3 successes, right? This is success times success times success, or 0.25 cubed is 0.016, right? So that's the probability of us getting 3 correct answers by guessing, right? So that's like what, 2%? Take that bet, right? Now let's say that we're gonna get 2 successes, success, success, and then a failure, right? That has a higher probability right there. So that would be 0.25 squared times 0.75, or 0.047. Call that 5%, right? That's more likely to happen, right? And then so on and so forth, right? Let's say that we get no questions correct. Damn, right? So that's going to be like 0.75 cubed, right? Which is going to be 0.422, right? So we have a 42% chance of getting nothing right. You know? So think about that before y'all be guessing on the test, right? Not this class, y'all other classes. You know? But if y'all are gonna guess though, when in doubt, choose B. So now we can compute the probability of R successes out of 3 trials for R equals 0, 1, 2, or 3. So let's compute the probability of 1. So the notation probability of 1 stands for the probability of 1 success for 3 trials, right? So there are 3 different outcomes that show exactly 1 success, right? So these outcomes are success on the first and failure on the second, failure on the first, success on the second, failure on the last, or failure on the first 2, and then success on the last, right? So since the outcomes are mutually exclusive, can't occur together, right? We can add the probabilities together. So the probability of 1, right, is going to be the probability of success on the first, plus success on the second, plus success on the last, right? Put them together, do the math, boom, 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 you got 0.422. Not so bad, right? Cube means to the 3rd power. So you're multiplying a number 3 times. So like, if it was like, say, give an example. Let's say I had like 2 to the 3rd power, right? It means 2 times 2 times 2, right? And 2 times 2 is 4, so 4 times 2, call that 8. And that's what cube means. Multiplying the same number by itself 3 times. But I'm building up to something here, though. Something real nice and powerful for all my iPhone users in here. So in the same way, we can find the probability of 0, the probability of 2, and the probability of 3. These values are shown in the table right here, where we have n equals 3. Sorry, and our probability of success is 0.25. R is our number of successes, 0, 1, 2, 3, right? The probability of R, right? Successes in this case, our R is 0, 1, 2, 3. You're just plugging it in, and boom, it's going to give us these probabilities right over here, right? So 0.422, 0.422, 0.14, 0.016. This is our table. And in the middle is the math, of how we get those answers. What? You have the formula already. Well, I'm getting to it though. We didn't get to it yet. Now you got all the sauce already for the whole class. I'm just explaining the sauce. That's all.
I'm going to find it as
You're gonna have to find this.
only that.
Yeah, that's what you're gonna have to find. So we have done quite a bit of work to determine the chances of R is equal to 0, 1, 2, or 3. Successes on 3 multiple choice questions if you are just guessing, right? So now we see that there is only a small chance, about 0.016, that you will get all the questions correct. All right. All right, so table 169 can be used as a model for computing probabilities of R successes out of only 3 trials. How can we compute the probability of, say, 7 successes out of 10 trials? We can develop a table for n equals 10, but this would be a tremendous task because there are 1,024 possible combinations of success and failure on 10 trials, right? Fortunately, mathematicians has given us a direct formula to compute the probability of R successes for any number of trials, right? So this is the sauce. This is what y'all have right now in y'all formula sheet. So who wants to do all that math that we just went through up here? I'm talking about like this stuff in the middle, right? It's mad work, mad work. All right. So here you go, right here. Bam. So this is our formula for the binomial probability distribution. So it says that the probability of R is equal to n factorial divided by r factorial times n minus r factorial times your probability of success raised to the number of successes, right? Times your probability of failure raised to the number of failure minus the minus successes, right? All on your formula sheet. Y'all gotta memorize this, all right? So where n, right, is your number of binomial trials, P is your probability of success on each trial, Q is your probability of failure, or 1 minus your probability of success. R is a random variable representing the number of successes out of n trials. So it's gonna be between 0 and whatever n is, right? Factorial notation, right, the exclamation mark, right? So what that means is that you're gonna be multiplying a number, right, in decreasing order from itself, right? So let's say 4 factorial that we have right here. 4 factorial is going to be equal to 4 times 3 times 2 times 1, or 24, right? Special cases, 1 factorial is equal to 1, 0 factorial is equal to 1, right? And then this right here is combination, right? N choose R, right? And this is the binomial coefficient. So it's going to be n factorial divided by r factorial times n minus r factorial. This gives us the values of the combination n choose R for select n, right? N being our sample size and R being our number of successes. Many calculators have a key designation for n choose R, and that gives us the value of n choose R directly, right? Great, right? Go ahead.
So where the little tiny r, the little tiny n, will you put it substitute a square root or a grid?
No, it'll be whole numbers only.
Oh.
Whole numbers only. Yeah. N is always larger than R as well, right? Because you can't have more success than your sample space. You know, that's another thing.
I don't need all this like this.
But you have to understand where they're coming from. Don't worry, I promise you, it's real simple. Real simple when you see it. So note, the binomial coefficient n choose R represents the number of combinations of n distinct objects, right? Where n is the number of trials in the case, taking R at a time where R is equal to the number of successes, right? And then let's look more carefully at the formula for probability of R. So there are two main parts, right? You have the expression P of R times Q raised to the n minus R is the probability of getting one outcome with R successes and n minus R failures, right? The binomial coefficient n choose R counts the number of outcomes that have R successes and n minus R failures. For instance, in the case of n equals 3 trials, we saw that in table 6.8 that the probability of getting an outcome with 1 success and 2 failures was probability of success times probability of failure squared, right? This is the value P raised to the R times Q raised to the n minus R, where R equals 1 and n equals 3. We also observed that there were 3 outcomes with 1 success and 2 failures, right? So we have 3 choose 1, which is 3. Multiply them together, and you have the probability, right? Hope y'all have your calculators. All right. So now what do we want to do? We want to compute, this is an example. We want to compute the probability of R using a binomial distribution formula. So privacy is a concern for many users on the internet. One survey showed that 59% of internet users are somewhat concerned about the confidentiality of their email. Based on this information, what is the probability that for a random sample of 10 internet users, 6 are concerned about their privacy of their email? Right? Let's take a look at that. So this is a binomial experiment with 10 trials. If we assign success to an internet user being concerned about the privacy of email, the probability of success is 59%, right? We are interested in the probability of 6 successes, right? So we have n equals 10, our probability of success is 0.59, right? Our probability of failure is 0.41, and we want our successes, right? So let's take a look at the formula and how we're going to do this. All right. This is the binomial probability distribution. So the probability of 6 is equal to 10 choose 6 times our probability of success, which is 0.59 raised to the 6th power, times our probability of failure, which is 0.41 raised to our sample size minus the number of successes, right? In the calculator, boom, 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 type it in, you get 0.25, right? So there is a 25% chance that exactly 6 out of the 10 internet users are concerned about their privacy of their email, right? You can type this all into your calculator, no worries, right? Good luck if you're using the iPhone. And this whole part of the lesson is for everybody that's using an iPhone, all right? For everybody else that actually got the calculator, I got you, because we're not doing this by hand. No, 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 no. All you got to do is just give me the answer and I'm chilling, right? So here we go. So many calculators have a built-in combination function on the TI-84 Plus, right? Which I think a lot of you might have, or at least I know you have it over there, right? You can press the map key button and then select probability, right? The combination feature is designated as n choose r, right? And then I have a figure here that's going to show you what that looks like. 1 second. Oh, I don't. Oh, well. It's going to look like n choose r on your calculator, right? For everybody else that got the right one, I'm going to show you guys how to do that in a second. All right. Let me just, give me 1 second. Just got to get a fake keyboard. 1 second. I need a nice picture. 1 second. This used to be a lot easier. Like I'm on Google looking for a picture, you know, to show y'all. Got you. All right, bear with me 1 second. Just want to get like a nice keyboard image. Then I can show y'all. I feel like whoever had that picture up just took it down. That sucks. All right, I'm gonna work with what I got. So take you. So It's distorted. 1 second, you guys, 1 second. I used to find this mad quick. And all of a sudden it's just like challenging. Well, the images I'm finding are distorted, which sucks. All right, I guess I'll take this. Something is better than nothing. Let's see how this looks. Oh my God, that was terrible.
Claro.
You think that'll help with it? Dang. So the projector is trash, but it's really, really clear on here. The light won't help. It's gonna still be distorted because it's distorted to me right now. I'm looking up here. So I'm gonna explain it, but go back on the recording and watch it. All right. Because it's like it's really, really clear on the recording, but it's trash up here. All right. All right. Long story short, right? So I want to do, let's say, combination in the calculator, right? What you're gonna do is you're gonna press. I'll tell you 1 second as soon as I find it. There's a button, right? Right here. It's if you look at the columns, you have like, say this is column 1, column 2, column 3, right? In column 3, it's the third button down, right? That's where you'll find the factorial symbol, right? You'll also find n choose r.
This one?
Yep, right? And you also find the permutation button there as well, right? So more specifically, the one that we're talking about, we want to do n choose r, where n is 10, and then we want the combination of r, which is 6, right? So to do it in your calculator, you will first press 10, then you press that button, a little special button right there. I believe the first time you press it, the factorial comes up, right? So you press it one more time, right? So we're gonna press that twice. So then now I think it comes up like this, NCR in the middle. Then you hit the 6. And then you hit enter, right? And then that gives you the answer.
210.
210, right? And that's how you find the first part of the binomial distribution, right? For yours, hit map, probability, right? And there you go. No, not that one. Okay. 10, map, probability, and then NCR number 3. That's it.
Thank you.
You're welcome. And then 6, enter, boom, right? So that's the first part. right, of the formula right there. And then the next part would be to take the 210, multiply it times the probability of success, which I forgot is what? The 0.59. So you could just say times, open parentheses, the 0.59. You could then use the caret symbol, well, not the caret symbol, I'm sorry. You can use this button right here to raise it to a power, right? So I'm in the first column and I'm 1, 2, 3, 4, 5 buttons down. First column, 5 buttons down, right? There's a button there that looks like X with a square on top, something like that, right? That's what you want to press to raise it to a power. And you can raise that to the 6th power times, over here is a 0.41. And then you raise that to the 10 minus 6 power, right? And that's how you'll get the answer that they got, which is 0.25. Got it. All right. That's fine. Yeah. Yeah. Well, for me, I don't like rounding, so you could just write everything, right? And then that'll be good. But this is one way that you can do it in your calculator, right? Okay. So now that we're done with that part, let's talk about the table, right? So I know you asked about it earlier, like if we got to use this table. So here goes the table right here, right? So using the binomial distribution table, all right? So in many cases, we'll be interested in the probability of a range of successes. In such cases, we need to use the addition rule for mutually exclusive events. For instance, for n equals 6 and the probability is equal to 0.5, right? What is the probability of 4 or fewer successes, right? So I'm asking, what is the probability of R less than or equal to 4? So which numbers are less than or equal to 4? We have R equals 4, R equals 3, R equals 2, 1, 0, right? When we want to add all of these together, right? The probability of 4, the probability of 3, plus 2, plus 1, plus 0, right? But we got to do that formula that we just did. That was just for one number. That was just for 6. We got to do that for every single one and then get all them answers and then add those together, right? Now, let's say that we don't want to do that. We got the table, all right? So here go the table real quick. All right, so it would be a bit of a chore to use the binomial distribution formula to compute all the required probabilities, right? Table 2 of your appendix, which you guys have, this is the table, right? The binomial table, gives values of the probability of R for selected p-values and values of n through 20, right? So to use the table, find the appropriate section for n, and then use the entries in the columns headed by the p values and the rows headed by the R values. Let's take a look real quick, because that might sound a little complicated. All right. So this is a little excerpt from your table, right? That you guys have. The table is the binomial table. It's the next page right over in your formula sheet I'm talking about, right? Where it says binomial experiments, right? So this is just like a little snippet from it, right? I'm going down to n equals 6, right? So for n equals 6, I have how many successes? I have 0, 1, 2, 3, 4, 5, 6, right? So this is my number of successes right here, my R, right? This is my sample size, my N, right? And then over here, these are my possible probabilities. Not all of them, this is just some of them, right? For our particular question that we're interested in though, let's take a look, right? We want to know what's the probability of 4 or fewer for a probability value that is 0.5 right here. When n is 6 and the probability of success is 0.5, we want to know what is the probability of 4 or fewer successes, right? So that being said, we can go straight to our table. We go to where n equals 6, right? I'm interested in 4 or fewer, so I'm interested in these number of successes here. So 4, 3, 2, 1, 0. All I have to do, go over to where the probability of success is 0.5, add up the numbers in this column, and that's the answer to the question. That's it. All right? So that's how you use the table, right? You look at where your number of successes are, match it with your probability of success, boom, and then just add whatever it is that they're asking you to do. All right? This is another way you can get your answers in this section.
So
Hmm?
on the test, how are you gonna word it? Oh,
So-
this.
You can decide if you want to use that, yeah. But the question would be worded something like, what is the probability of, let's say, fewer than 5? Or 4 or less, things like that. And then you just add up the numbers. That's it. Probably, hold on, let me see something.
Yes.
All right, so we not meeting next week, right? We definitely got a couple more topics to do. So I'm thinking about either October 26th or November 2nd. Yeah, that's probably gonna be test 2. Yeah. One of them 2 days. Like it depends on like how much we cover and if we get there quick enough, stuff like that. Just probability, right? So what we did last week, we met last week, right? Yeah, last week, and then this week, and right. So basically, like we've moved from descriptive statistics, and now we're in inferential statistics, right? This is the beginning of inferential statistics. Let's talk about the table a little bit. So table 610 is an excerpt from table 2 of the appendix showing the section for n equals 6. Notice that all possible R values between 0 and 6 are given as row headers, right? The value P equals 0.5 is one of the column headers, right? For n equals 6 and P is equal to 0.5. You can find the value of the probability of 4 by looking at the entry in the row headed by 4, right? And the column headed by 0.5, right? That's the probability of 4 right there, 0.234, right? All right, likewise, right? You can find other values of the probability of R of the table. In fact, for n equals 6, probability of success equal to 0.5. So we have probability of R less than or equal to 4 is going to give us a 0.234 plus 0.312 plus 0.234, et cetera, et cetera. Add them together and you get the 0.890, right? So you're just adding up that column that I showed y'all, right? Alternatively, to compute the probability of R less than or equal to 4, excuse me, for n equals 6, we can use the fact that the total of all the probability of R values for R between 0 and 6 is 1. And the complement rule, so since the complement of the event r less than or equal to 4 is the event r greater than or equal to 5, right? We could have used this formula where we say that the probability of r less than or equal to 4 is equal to 1 minus the probability of r minus the probability of 5 minus the probability of 6, right? And you just get the 5 and the 6 off the table, boom, boom, subtract them, and we get the same answer, right? So you can either add up what they're looking for, or you can find the complement of it and go in reverse, right? And you'll get to the same answer, right? Up to you guys what y'all want to do. Just give me the right answer. That's all I care about, right? In table 2 of the appendix, probability entries of 0.000 do not mean that the probability is exactly 0. Rather, to 3 digits after the decimal, the probability rounds to 0.000, right? So when you're looking at the table, you're going to see some probabilities that's like 0.000. That doesn't mean the probability is 0. It means that it's rounded off to that, right? So if you did it on your calculator, you would see that there's more numbers to it, right? It's just that the first 3 numbers, or actually 4 numbers, are 0, right? That's what that means. So because of rounding the binomial probability table, probabilities computed by using the addition rule directly might differ slightly from computing probabilities computed by using the complement rule, right? Just a little bit, just a little bit. And the reason for that is because the table itself is rounded, right? The table itself is rounded. So now using the binomial distribution table to find the probability of R, let's look at this example. A biologist is studying a new hybrid tomato. It is known that the seeds of this hybrid tomato have approximately 0.7% chance of germinating, right? So 70% chance of germinating. The biologist planted 6 seeds. This is a binomial experiment with n equals 6 trials. Each seed planted represents an independent trial, right? So we say that germination is success. So the probability of success for each trial is 0.7 or 70%. So n is equal to 6. That's how many seeds are planted. The probability of success is 0.7 or 70%. The probability of failure is 30%, that they won't germinate at all. And we want to know what's the probability that 4 of them will, right, out of the 6. All right. So let's take a look. So we wish to find the probability of 4, right? The probability of exactly 4 successes. So in table 2 of the appendix, find a section where n is equal to 6, right? The excerpt is in the table 610. Then find the entry in the column headed by P is equal to 0.7, right? So we're looking at the table, look for where 0.7 is, and the row headed by 4. And then you'll find that this entry is 0.324, all right? Let's take a look at that real quick. Give me 1 second. Just bring that up. So looking at your formula sheet, just trying to bring this up, want to show you guys firsthand what we're talking about. All right. Give me 1 second. A little smaller. So that's your header right there, right? And then I want to go down to 6. 1 sec, this is. All right, so I'm kind of just putting it all together real quick for y'all. Let me just make this a little bit smaller. One second, you guys. Hold on.
What page is the formula sheet?
This is on the that one right there that you're looking at, the other side. That's it. Right. One second, we're over here freezing right now. Give me 1 second. Okay. This be happening from time to time. Oh, why is this not responding? Bear with me 1 second, you guys. Bear with me 1 second. I don't know why this be freezing up on me like this. I'm trying to show y'all how to look this up. All right, hold on 1 second. Let me see if I could just like cancel this out. Just open this back up. 1 second, you guys. 1 second. Sometimes when you put too much into it, it just like starts freezing, you know? All right, let's try that again. Boom. All right, cool, cool, cool. All right, give me 1 sec. Let me get that header. There we go. All right. And let me get that 6 real quick. All right, that's perfect. All right. So what we're trying to do, right? For n equals 6, right? This is our, what you call it, our sample size right here. Let me get back my color. 1 second. For n equals 6 right here. It's our sample size, right? We want to know what is the probability of r equal to 4, right? And this is where our probability of success P is equal to 0.7, right? So looking up here, we have a whole bunch of different probabilities of successes up top right here, right? I'm interested in 0.7, right? So here goes 0.7, and I want to know what 4 is, right? And then what we do is look at where they intersect that, right? Look at where they intersect that. And then this is my answer right there.
What, 0.08?
Point, well, 0.324. That's it. Right?
So the probability is zero, if they give you the probability of 0.7, right, and then it's R equals 4, then you go on the 4 here and stuff.
Right, and then you just find where they intersect that. And this number, 0.324, is your answer to the question. So this is the likelihood that out of 6 trials, right, or the 6 seeds that we planted, right, 4 of them will germinate. This is the likelihood of 4 of them actually growing, right? And that's it. That's how we look it up on the table, right? If they ask you a question like, what's the probability of R less than or equal to 4, like in the previous example, you add all of them, right? But not all of them. You just add up this column. Exactly, which would be these right here. And then that's it. Whatever the sum of those are. Just add them up in the calculator and that's it.
If they ask what, TV is what?
The probability of R is less than or equal to 4. For example. So let's keep it moving. Oh yeah, a lot more. I didn't even get to the good part yet. All right. So what is the probability that at least 4 seeds will germinate? Solution. In this case, we are interested in the probability of 4 or more seeds germinating. This means that we are to compute the probability of R greater than or equal to 4. Since the events are mutually exclusive, we can use the addition rule. So the probability of R greater than or equal to 4 is equal to the probability of R equals 4 or R equals 5 or R equals 6, which is equal to the probability of 4 plus probability of 5 plus probability of 6. We already know the value of the probability of 4, right? We need to find the probability of 5 and the probability of 6. Use the same part of the table, but find the entries in the row headed by R equals 5. And then the R value for 6, right? Be sure to use the column head by the value of P for 0.7. So basically, I'm looking at these two numbers right here. Hold on, I should have used a different color. Sorry about that. I'm looking at these two numbers right here, right? That's the 0.3003 and the 0.118, right? So the probability of 5 is equal to the 0.303, and the probability of 6 is equal to the 0.118. Now we have all the parts necessary to compute the probability of R greater than or equal to 4. So we know what the probability of 4 is, 0.324. We're going to add the 0.303 plus the 0.118 to get 0.745. All right? So we're just adding numbers off the chart. That's all it is. All right. Let's throw some meaning behind this. What does a binomial probability distribution tell us, right? So when a binomial probability distribution is used, we know the sample space of events consists of a fixed number, n, of binomial trials. This means that the trials are independent and performed under the same conditions, right? There are only 2 outcomes for each trial, binomial, right? So 2, success and failure. The probability of success on each trial is the same and is designated as P. The probability of failure on each trial is designated as Q, and Q is equal to 1 minus P. On your formula sheet, you have that right there. Look at the top, right? The binomial probability distribution, right, gives the value of the probability of R, right? Where the probability of R successes out of the N trials for each R between and including 0 and N. The calculation of the probability of R depends on the probability of success on each of trial, the value of R, and the value of N. Right? So that's what all of this stuff means. All right, here's a sweet spot. Right? All of that probably sounded like a whole lot of work, right? Here's the good news, your calculator could do it all. Right? So using technology to compute the binomial probabilities, some calculators and computer software packages support the binomial distribution. In general, these technologies will provide both the probability P of R for an exact number of successes R, and the cumulative probability of R less than or equal to K, where K is a specified value less than or equal to the number of trials N. Note that most of the technologies use the letter X instead of N for the random variable denoting the number of successes out of N trials, right? So long story short, this whole thing that I just showed y'all with the table and all of that stuff, if y'all ain't want to do it, y'all can just type it in the calculator, click enter, and write down the answer, right? This is how you do that. This is the sweet spot. So check this out. So the software packages, Minitab, I don't even know what that is, Excel, as well as a TI-84, right? And the Inspire, right, calculators include built-in binomial probability distribution options. These options give the probability of R of a specific number of successes R, as well as the cumulative total probability for R or fewer successes, all right? TI-84, right? To do this, you press the distribution button on your calculator, DISTR key, and then you scroll down to where it says binomial PDF, right? Binomial PDF. And then the binomial PDF you're going to type in is NPR. Now, your calculators are a little bit more advanced. They have a GUI system in it, so it's going to specifically outright give you an option to enter in the N, the P, and the R, right? I'm going to get to the 36X Pro in a second, right? This is for the graphing calculator, right? So you're going to enter the number of trials N, the probability of success on a single trial P, and the number of successes R, right? And this gives you the probability of R. So you remember that big formula that we started off with, right? The one with N choose R times P to the, let me write it real quick. Yeah, this is this one. I felt like y'all got it. This one, N choose R, right? Times the probability of success raised to the R times the probability of failure raised to the N minus R. That's this formula right here in the calculator. All you have to do is hit enter and get the answer, and then you're done. That's simple, right? Now, let's talk about that table, right? If you enter, so for the cumulative probability, right, that there are R or fewer successes, we have the binomial CDF, right? So for binomial CDF, right, this one right here, remember when we were doing the chart, and we were adding up all the numbers in the chart, right? This one function right here in the calculator does it for you. Straight, boom, and it gives you the answer. Right, so that's adding up all the numbers in the chart, right? But you have to know when to use it. Yeah. The cumulative, right? Cumulative distribution function is what it stands for, but don't worry about all that, right? All you need to know is that that's the probability for R less than or equal to some number we're gonna call K. Right? Now, let's say that I want to have a conversation. I wanted to do the probability of a number greater than K, right? The number is bigger than K. Well, the numbers on the bottom,
Yeah.
right? Yeah. So what you would do is you actually do the complement of it, right? So if you do 1 minus the probability of R less than or equal to K, that's going to give you the probability of R greater than K. That's how you do the flip, right? So basically, in your calculator, you're going to take the number that the calculator gives you, and you're going to take 1, you're going to subtract it from 1, right? So in this case, right, this is the probability of R less than or equal to 4. So this is 4, 3, 2, 1, 0. Add it up, right? If I wanted the probability of 5 and 6 together, right, all I have to do is 1 minus this number, and I got the probability of 5 and 6 together. And that's it. Good stuff, good stuff, good stuff. All right. Let's look at the rest of your calculators. The TI 36X Pro. Give me 1 second. Let me get back that picture. Oops, wrong one. All right, again, this is going to be blurry on the projector, but go back into the recording and you could take a look. It is crystal clear in the recording. All right, this image. Make that a little bit smaller. Actually, I'm gonna do this a little bit bigger. All right, that's good. All right, binomial expression in this, right? So I'm looking for the probability of R equal to some number. I'm just gonna call it K. This could be any kind of number, right? So in your calculator, you're gonna press second, right? And second is I'm gonna use the rainbow color real quick because I realize that it's not gonna pop on the calculator if I don't do that. So you're gonna press second, right? So second is the blue button at the very top, this thing right here, that's second, right? Then, and also let me explain something too. Anytime that you hit that second button, it activates all the blue that you see in the on top of the buttons, right? The baby blue, right? I'm looking specifically for this button right here, right? So this is the data button, which is, let me count, hold on, it's the third row, second down, right? So you're hitting this button, and then what you want to do is you want to go across to where it says DISTR, which is short for distribution, right? And then go down, and we're looking for binomial PDF. You guys see that? You got it? Cool. So just go down. Let me see real quick. Take a look at you. Go across the distribution first, and then go down. So second, data. That one.
That's the one number 4.
Second. Then go down to distribution. It's number 4, you said?
Number 4, yeah.
All right, so I just heard it's number 4. So Somebody told me it's number 4 in the class. I'm gonna just put 4 right here, right? You can either go down to 4 or you can literally hit the number 4 in your calculator and it'll work, right? So when you hit it now, it's gonna ask you for your trials at the top, right? Trials is another name for n, your sample size, right? In our case, our n was what? Hold on, I forgot. And it's 6, right? So you guys can enter in 6 right there, right? Right underneath that is going to ask you for your probability of success, right? Or does it just say the word success? I can't remember.
Success equals 1.
Success equals 1? Let me see. So CCESS. So for us, right, our success, we want to enter in, I'm just copying from the one above, right, is 0.3. And then I believe it's going to ask you for an X,
Yeah.
right? X is your number of successes, right? In our case, it's 4 that we're looking for, right? So what we're looking for is what is the probability that R is equal to 4, right? When P, which is success, is equal to 0.3. And then enter. And what's the answer?
0.05955. That's the value?
555. I'll take it. Yeah. Notice
535.
35.
No, 0.059.
Wait, 0.0.
5.
What else?
535.
Okay. Notice though, it's the same thing that we got up here, right? So that's our answer in the calculator. All right, that's how you do it in the 36X Pro. All right. Let's flip the script a little bit. Let's flip the script a little bit, right? So now, let's say I want to know what is the probability of R less than or equal to 4. So now what am I asking you? I'm asking you what's the probability of 4 plus 3 plus 2 plus 1 plus 0, right? All of them, right? So probability of 4 plus probability of 3 plus probability of 2 plus probability of 1 plus the probability of 0, right? I want that answer. So in your calculator, right, you're going to go to, same thing, right? We're going to go to second, right? And then the data button, right? And then you're going to go across to distribution, right? But now you want to go down to the number 5, right? Binomial CDF, right? So let me write it right here. So second, right? And then you want to go to where it says stat regression / distribution. That blue part above, you want to go across to distribution, right? And then you can either go down to 5 or you can just hit the number 5. Your choice. Go down to 5 or hit the number 5, right? This is for binomial CDF, right? Binomial CDF, right? And then now it's going to ask you for what? It's going to ask you for your trials. So it's going to say, what is my trials? Remember that trials is short for N, and that's going to be what? 6, right? And then they're going to ask you, right? What is your number of successes, right? Right. I forgot what it says. Is it like P of success?
Yeah.
P of success, you're right, yeah. So that's 0.3. And then X, which will be your number of successes, right, is going to be 4. And then you hit enter. And that's it, 0.989, whatever, right? And you see that that's the same answer that we got up here, right? So this is all those numbers added up, 4, 3, 2, 1, 0, right? Without you having to look it up in the table, right? Your choice of how you want to do it. All right. Again, in the recording, this is going to be very, very clear. I know it's like really, really shitty right now up here, but it's in the recording. All right. All right, we almost done, almost done. All right, so many times we are asked to compute the probability of a range of successes. For instance, in a binomial experiment with n trials, right? We may be asked to compute the probability of 4 or more successes, right? So table 611 will show that, right? Common English expressions is 4 or more successes translates to inequalities involving R, right? And we remember how to do that. You just simply take 1 minus, right? 1 minus the probability of less than or equal to, and that gives you the answer for greater than, if you're using the calculator. All right. So I just want to cover some vocabulary with you guys a little bit so you guys can kind of see what could come your way, like on the homework or a test. So common English expressions and corresponding inequalities. Consider a binomial experiment with n trials and R successes, right? So the expression 4 or more successes, that means R greater than or equal to 4. At least 4 successes, right? That also means R greater than or equal to 4. No fewer than 4 successes is R greater than or equal to 4 as well. And not less than 4 successes is also R greater than or equal to 4. Let's say that I wanted to do R less than or equal to 4. It could be read as 4 or fewer successes. It could also be read as at most 4, right? At most 4 successes. No more than 4 successes is also R less than or equal to 4. The number of successes does not exceed 4 is also R less than or equal to 4, right? Let's say that I want R just generally greater than 4, right? So greater than 4 means that 4 is not included, right? 4 is not included. So that would be like, for example, more than 4 successes, or the number of successes exceeds 4, right? That's how it'd be worded in the question. Let's say that I wanted it to be less than 4. So the number is less than 4, not including 4. So we're talking about like 3, 2, 1, 0, right? So that could be read as fewer than 4 successes, or the number of successes is not as large as 4, right? So this is how some of the questions that you might come across will be worded and what the appropriate response would be to them, right? It'd be like that. Like, what is the probability of 4? Yeah, just like that, like flat. Yeah.
Are you sure?
Yeah, simple. Like when it's a specific numbers, they're just gonna flat out ask you for it. Yeah. So often we're not interested in the probability of a specific number of successes out of n binomial trials. Rather, we're interested in a minimum number of successes, a maximum number of successes, or a range of a number of successes. In other words, we are interested in the probability of at least a certain number of successes or no more than a certain number of successes, or the probability that the number of successes is between 2 given values. For instance, suppose engineers have determined that at least 3 or 5 rivets on a bridge connector need to hold, right? If the probability that a single rivet holds is 0.8, and the performance of the rivets are independent, then the engineers are interested in the probability that at least 3 of the rivets hold. Notice that the probability of R greater than or equal to 3 rivets hold is 0.943, while the probability of R equals to 3 rivet hold is equal to 0.205. the probability of at least 3 successes is much higher than the probability of exactly 3 successes. Safety concerns require that 3 of the rivets hold. However, there is a greater margin of safety if more than 3 rivets hold. As you consider binomial experiments, determine whether you are interested in a specific number of successes or a range of successes. Right? And then one last comment, real quick. Not gonna ask you guys this, but this is more for, when y'all go to the 4-year school, y'all know what they're talking about. Sampling without replacement. All right, so using the hypergeometric probability distribution. If the probability is relatively small and we draw samples without replacement, the assumption of independent trials is not valid, and we should not use the binomial distribution. The hypergeometric distribution is a probability distribution of a random variable that has 2 outcomes when sampling is done without replacement. This is the distribution that is appropriate when the sample size is so small that sampling without replacement results in trials that are not even approximately independent. All right. This is just for y'all knowledge, for going to the 4-year school, not asking you this. All right. That being said, that's it. Start your homework. All right. May I take this down? Thank you, thank you, thank you. All right, so everybody watching the recording, have a great week. Talk to y'all another time. Pantry this week, no class next week. All right. Have a good night, y'all.